I'd like to start by thanking you all for coming as well, and my committee for jumping through a lot of loopholes and a lot of reschedulings again and again to keep here. Want to turn off the lights, or we're fine? Okay. So first of all, the title of my presentation is Divergent Behavior with Convergent Evolution: Common Garden Experiments with Desert Rodents and Vipers. So I'll get into a little bit of what I'll be talking about, a bit about the evolutionary theory of constraint gradient adaptations and evolutionary convergence, then go into some predictions of what these experiments, and I will probably talk in the formal we because there were so many people involved in this project. It's easier for me. We're used to talking about it that way. So the predictions we had is the experimental design in brief, and of course a lot of the results and the major findings that this research opens up. So first of all, what is evolutionary convergence? Evolutionary convergence is the idea that similar environments will produce species with similar traits. And as you can see on this slide here, we've got a mole rat, a giant mole rat in Ethiopia, which in essence is a marmot from the northern hemisphere. Okay, there are no marmots in Africa, and as a result, something else stepped up to the point and evolved to be the marmot of Africa. So how did that happen? Well, we had high elevation, alpine grasslands, and a mixed glacial till substrate, and as a consequence, we have a species that makes itself the best at using those resources. Claws for digging, incisors to dig up tubers and roots, and of course, social living that gives it protection from predators, and also an ability to thermoregulate when hibernating in the cold winters. If we look at another example, if we've got a riparian vegetation environment with rivers, some muddy banks, an assortment of fish to eat, well, you're going to give them a mammalian predator that will specialize on that environment, with a wide tail to swim, webbed feet to help swim as well, and only fur that repels water so it doesn't get cold. However, you don't have otters everywhere, okay? And in Australia, we got the giant water rat from the rat family that stepped up to the plate and became the otter of Australia. However, what happens if you've got two of these species, similar ones, that end up in the same environment together? Okay, so here's an example. Of course, you already know what happened there. When we've got the ichthyosaur and the dolphin that both evolved in the same environment. Given some environmental change, disturbance, we have one of them that went extinct. Presumably, if the otters arrive into Australia, the giant water rat will not have a good chance of surviving. So how does an animal actually arrive, or a species arrive, into this new environment where it comes in contact with its competitor of the same evolutionary niche? Well, there's a few interesting papers that predict on how that can happen and what would happen once it actually occurs. So first of all, Pinter et al. In 2011 had said that an animal can invade a system mainly if it has an equal or better strategy at using the resources that are originally there. Okay, so if the otter is a better predator than the river rat is, the water rat is, it will be able to invade that system. Once a species actually comes in, the better competitor outcompetes the one that's already there and causes this extinction. And lastly, once we have an invasion that actually occurred into a system, the whole community changes in its perception, in its trajectory of evolution towards a new ecological stable strategy, towards a new optimum. So the systems we were working with are very similar systems. We have the Negev desert dunes on one side and the Mojave desert dunes on the other. I had a flag which disappeared for some reason. Anyway, so as you can see, the environments look very, very similar and have very similar communities. Both of them have a sidewinding viper. In North America, we've got the sidewinder rattlesnake, that is a pit viper. And in the Middle East, in Israel, we've got the Saharan horned viper, Cerastes cerastes. As you can see, they're very similar looking snakes. In the Negev, in addition to that, we also have a community of carnivorous rodents. We have two species of gerbils, which we've been working with for many years. Gerbilis allenbii and Gerbilis pyramidum in Israel, so the Allenby's gerbil and the greater Egyptian sand gerbil, and the desert pocket mouse, Pterodictis penicillatus, and the kangaroo rat, Merriam's kangaroo rat, Hippodomus merriami. On top of that, we've got two predators which are the same in both of these systems. The same species, Tito alba, the barn owl, exists both in North America and in the Middle East. And the red fox, there is some occurrence of it also in the Mojave Desert. However, other species of foxes are more common in the Mojave. But one thing is very clear. The North American species have constraint breaking adaptations, some kind of an evolutionary tool which is more sophisticated than the species in the Middle East. So in the case of the snakes, the vipers, we see that the pit vipers had heat sensing ability. They can see in dark nights, and you can see in this photo here, this is actually a snake holding a mouse in infrared vision. This is the way it would look to the snake on a dark night when there is no moonlight outside. The Negev desert snake, besides the Saharan horned viper, does not have heat sensing ability, and as a consequence uses a different strategy for hunting. It does not point out the snake. It digs itself in the sand and waits for a rodent to step on top of it. So what do we expect it to see? What do we want to find here in these experiments? And we're looking predominantly on the rodents and the way they perceive the environment, and the environment as a factor of the predation risk within it. So first of all, if we're looking at the new moon phase, when there's no moonlight, you can see that we have the snakes from North America that can see them. So we're presuming ahead of time that the North American rodents will perceive this time of the months as more risky if there are snakes around. From other experiments done before, Kotler et al. In 1993, they showed that the gerbils, this is Gerbillus allenbii, one of the species we worked with, perceive the new moon as a safe time because the snakes are not active during that time, so they can take advantage of the food patches that are there. Also, when there are snakes around, the research before, lots of different papers from Joel here, from Amos Busquila, and multiple papers by Bert Kotler, have shown that when there is vipers around, the rodents move out of the bushes, both in North America and in the Middle East, out of the bushes and into the open area, where they're actually safer. However, if we do add owls into the system, then the open habitat becomes really, really risky. And the bushes, even though they have vipers in them, are still safer because the risk of predation from an owl is greater than that from a viper. You have a lower survivorship rate. So the experimental design, we had each of the population of rodents was facing multiple predators in 3 different stages. First, entry interviews, where we asked them to see what is your perceived knowledge of the vipers before you start experimenting and actually getting a risk of predation hands-on. Then we had common guard experiments, which I will talk about briefly soon. And then we repeated the first step to ask those rodents, have you learned anything? Did you change your perception of risk from those predators? So the interview chambers, in which the animals were, the populations were interviewed or asked about the perceived risk of predation at the beginning, is a combination of 2 systems. A Y-maze type of system, which tests, usually in a binary setting, which do you prefer, A or B. And combined with that, optimal foraging theory, an optimal patches theory that was devised by Joel here, that says that an animal will stop foraging when the risk of predation, based on the risk of predation, to manage the energetic value that it can get from the food in the patch. So we call that a giving up density. So we have, in essence, testing 2 things. First of all, a choice of which of the chambers, which of the rooms of the chamber that the animal prefer to go to, and also what level and how the different vipers compare to each other within that system. For the common guard experiments, which was sandwiched between 2 interviews, we have an idea, which this is an enclosure called the vivarium, which is a large experimental semi-natural arena we have in Sde in Israel, where we can choose what species interact with it, with which. In other words, similar to your common garden at home, where you have your petunias and you want them to interact with your geraniums, we chose to put our rodents with specific predators we chose. We were able to control the interactions of the different species with each other. This enclosure, which is 17 by 34 meters in size, had 12 patches per quadrant. Each quadrant had a different snake treatment and had gates that allowed the rodents to cross by, but not the vipers. They were S-bend shapes that had spikes in them, which stopped the vipers from putting pressure on it and moving through. In one of the experiments, the first experiment was Gerbilis allenbii, we had a little bit of a different setting here, where the two predators that were added on top of the vipers, the fox and the owl, were only divided into one side of the vivarium. And that is important. I'll talk about just a little bit afterwards, because of an experiment that Ken and Annabelle was running simultaneously with my experiment, and allowed us to run multiple things together. After that, we changed the setting a little bit to make statistical analysis easier for the rest of the chapters. So what would you actually find? What are our actual results? For our interviews, at the beginning, we find that all the different rodents, except for Chirodopus spinicillatus, the pocket mouse, feared their own viper, their known viper, which is in the white background, as opposed to the novel viper in gray background, more than the novel viper. They said, we know this viper, we don't want to be next to it. However, this new viper, we're not sure about. We'll take some risk in its presence. Chirodopus spinicillatus, on the other hand, just avoided vipers in general. So in these experiments, we had a total of 1.5 grams of millet for them to forage in the trays. And what you can see is that they barely touched the seeds at all. So on average, these animals barely touched the seeds and it just avoided the predation risk at all costs. Then some of the commonalities that we found between those different rodents. So first of all, we asked in a spatial analysis, how do the different rodents view our environment? So this is now talking about the common garden experiments. Did the environment look the same to all different rodents? We found that using ranking, that all the different rodents viewed eye to eye on terms of what areas of this vivarium, this enclosure, are risky and which ones are safe. We also found that they all manage the microhabitat in a similar way, some more significant statistically and some more of a trend. However, these general patterns repeated themselves to all of 4 species. First of all, on the baseline, the bush is safer than the open environment. However, when we add the snake in there, the vipers in there, then the safe environment before turns risky and the open becomes safe. So they did manage that in that same manner. But if we add the owl, immediately the open becomes way more risky than the bush with the viper. So they move back under the bushes when we add an owl. Sometimes we found something that Karen is listening right now also, that owls can be quite stealthy and change their behavioral patterns. This example of an owl under a creosote bush. If we're looking at how the animals perceive the landscape, and as it changed, the fear in the landscape, and as it's changed with the owl and without the owl, we find that 2 of our species, the North American ones, Chirodopus spinicillatus and Chirodopus merriami, had a linear pattern in which they responded to the fear level. In other words, each of these dots on the map shows you the same trait on nights with owls and on nights without owls. What's the giving up density? A higher giving up density means higher risk. And in this case, what we're seeing is that both the North American species have a linear pattern that with added owls, the landscape just rises, the fear just rises. The 2 Middle Eastern gerbils have no significant patterns, and we cannot actually see any linear increase with the risk of owls. What does that actually mean? A few things. So first of all, let's look at the North American species. This is Chirodopus spinicillatus, the pocket mouse. Generally speaking, a very fearful species. It avoids foraging altogether. In red, this is a high giving up density. In low, this is a safe area. So green and blue are safer environments. And as you can see, the species fears the environment in general. However, when you add the owl in, the whole landscape just rises. Areas that were risky remain risky. Areas that were safe, some of them become riskier, and some remain safe. However, in general, the pattern of the landscape is the same. What is also interesting is the angle of change between the safe areas and the risky areas becomes much more steep, which means it's a much more verbose landscape, and they're moving from safer to riskier at a much shorter distance. With the kangaroo rats, on the other hand, these are risk-taking species. As you can see, they forage everywhere, and the whole environment is relatively safe to them. They don't perceive a lot of risk in the environment with vipers alone, but that increases a little bit, yet still showing significant risk-taking behavior with the owls in the environment. Similar, again, we see the pattern of the areas that were risky remaining risky, just going up in elevation. What did the gerbils do? They came in with a different perspective, a different pattern of change of behavior. The areas that were safer for Gerbillus allenbii, sorry, they're riskier for Gerbillus allenbii, became safe when the owls were in. The whole map changed completely on nights with owls as opposed to nights with only vipers. So they reassessed the landscape and measured it by the risk of the owl and not by the risk of the vipers. The larger gerbil, Gerbillus pyramidum, did a very similar thing. It reassessed the landscape as well. The landscape that had islands of risk, areas that were risky, but all the rest was areas they could harvest in and forage in, became areas of safety. So we changed the islands of risk to a pattern of islands of safety. Those two maps are not at all the same, and there is no direct linear trend, as you can see from before last slide. So now we looked at this pattern in the spatial scale. Let's now look into the overall signals that these rodents were telling us about what they perceive of the risk in the environment. So did the rodents actually respond, as we predicted, to the different predators? So first we'll look at Gerbillus allenbii, which had that different design a little bit. So this design showed us that we had a direct effect on one side, where they actually experienced the foxes and the owls, and the other had only vipers. Okay? What we can see is that on top of the whole bigger scale, even though the owls and foxes are not coming in direct contact to them, they're still responding to them being across the fence. They can see them, and they're sensing that their presence is around. It's not as clear as a signal as when they're actually coming into contact with it. So it's a spillover effect. Indirect contact, it is very clear that to the gerbils in that specific experiment, which is a little bit contradictory to other findings, other experiments that were run in the Kotler lab in the past have shown, the foxes were scarier to the rodents than the owls. However, the specific fox we were using in this experiment did tear up a lot of the experimental design and was digging up burrows, so it's completely understandable why they were responding the way they did. I would be very scared too if my house was bulldozed multiple times a night by this fox. If we're looking only at the owls, so the effect that the owls had with the vipers, you can see there's a clear viper effect without the owl. The vipers alone are very scary. No vipers can take advantage. But that whole effect is, again, dampened down by the owl. The owl takes more risk effect than does the snake exhibit. In other words, the minute we have that, the difference between the control and both vipers together was very, very small. In a spillover, that gives us this pure one viper versus the other. We found that the gerbils fear the snake they knew more than the novel viper. In a comparison between North America and the Middle East, we find a few interesting trends. So first of all, this graph shows you the full moon versus the new moon. So this is lit conditions. In the full moon, there's a lot of moonlight, and in the new moon, little moonlight to no. And what we find here that's very, very interesting, first of all, is we have a little bit of a caveat to talk about, is why the control had such high fear levels in the Gerbillus pyramidum experiment. And that is due to the owls that had a very strong predation in that specific quadrant. So I had 5 rodents get eaten by those owls in that quadrant. As a result, that was biasing the results we were seeing. What we can see, though, is that the patterns of behavior are as predicted to the different populations of rodents based on the environment they evolved in. So the Israeli rodents, the gerbils, feared the full moon, where there are moonlit conditions, more than the new moon conditions where they take advantage, no matter what snake it is. Which means they were not really perceiving the fact that these pit vipers had infrared vision and could see them on dark nights. The kangaroo rats had the opposite trend. To them, the full moon was safe and the new moon was risky. So again, exhibiting patterns as they would and have been shown to exhibit in their native environments in Arizona. Additionally, both of the rodents feared the novel viper more than the viper they evolved with. So these trends are kind of opposite. If we're looking at Pitodipus penicillatus, so the pocket mouse, this was kind of a neurotic rodent. They feared going out and foraging in general. With a total of 3 grams of foraging out in the environment, these rodents preferred to give up their meals altogether than go out and forage. What is interesting is, first of all, the patterns are identical to the patterns of moonlight based on the time of months was identical to that of the kangaroo rats, and the fact that they preferred foraging in the new moon than in the full moon than in the new moon. So they viewed those as safer. What is interesting is the pattern of change over time in these rodents. We expected them to learn to fear the horned viper or lose the fear of them a little bit based on the fact that, especially in the new moon, because they cannot see them in that hard time of the months. What we found is an increased fear during that time of the months and a decrease when they should be actually at higher risk because these snakes are active. And lastly, coming out of the experiments, we reintroduced the rodents and asked them, did you learn something about the different predators you were exposed to? So first of all, we see that both the gerbils learned to fear the vipers that are novel to them. They fear them now at least as much as the vipers that they did evolve with. What was very interesting as well is the Podomus mariamide, the kangaroo rat, lost all the respect to this novel viper. They say, I realize that in the dark conditions of these chambers, you're not a risk to me. So they actually foraged even more in front of that viper than they did in front of the cage without a viper at all, so the control. And lastly, Pitodipus penicillatus remained fearful altogether. So again, this neurotic population said, there's vipers around, I'm not coming out at all. So what do those findings actually tell us? What's the meaning of these experiments? What do they show us? So first of all, these rodents that appear to be convergent, at least in looks, in physical appearance, in their diet choice, in the habitat, in the way they live in the habitat, in the use of the habitat, didn't actually behave the same way. They didn't have the exact same patterns, and they did not follow the predictions, at least a lot of our predictions, as we expected them to be. The North American rodents that evolved with a more sophisticated predator. So it may not be specifically the sidewinder rattlesnakes we use, but they did evolve alongside a lot of pit vipers that can see them in dark nights. And as a consequence, we see that being that is the big difference in terms of the community in North America versus the Middle East, the patterns are fixed towards extremes. If we're looking at the kangaroo rats have the adaptations, the physical adaptations to handle predators. They're very good on 2 feet. Okay, they're very bipedal. They can jump out of harm's way. They can jump backwards from a viper, and they can jump sideways to avoid owl predation. The pocket mice, on the other hand, that don't have the physical adaptations, just change their behavior or adapt it to a behavior that says the minute there is risk, I'll forego the risk altogether. So they avoided the risk in the environment. And given the adaptations, you can see that once the one that had the adaptation, the physical adaptation to avoid snakes, it says, I realize, I reassessed this viper now. I reassessed the viper that is not what I know it to be. And now I'm willing to take the risk of it because I know how to handle it. So that was a change in perception. On the other hand, the rodents of the Middle East evolved as a less lethal predator. And they showed a much higher plasticity in the behavior and assessing the patterns of predation risk within the environment. Be it the owl change, completely changing the landscape and reassessing the way they view the landscape, or between the vipers, reassessing the risk and adapting their behavior in response quite rapidly. If we're looking at the question of, is there really an advantage to those pit vipers over the horned vipers of the Middle East? Well, just in success rates, and this of course is not very strong statistically, but it's just an interesting curiosity what we did find, is there were 9, or actually 8, rodents that were eaten by the Saharan horned viper during the experiments. So considering we had, it was about 70 rodents went through these experiments altogether. Okay, so 8 of them got eaten by the horned viper. Only 1 rodent, one Drobillus pyramidum, was eaten by a sidewalker rattlesnake. So this adaptation may give them an advantage theoretically. It didn't directly translate to what we saw in the field. All these experiments could not have happened without a lot of help. First of all, my advisors who were there helping me for 5 years, giving good advice, helping me understand, get all the background knowledge for this, and really supporting me both financially and of course, was all the learning process and my own personal growth through this. My committee, my collaborators, especially Karen Embar, who shared all the work in this experiment, the technicians who did a lot of the work and helped a lot on nights and sorting data, and of course my friends and family who were there supporting, helping me do some linguistic editing to all these things I've written, and were always there helpful around. Thank you.
We have plenty of time for questions, but I'm going to ask the committee to withhold their questions until we get over to SPS. Otherwise, the floor is open.
Yeah. So how does something that's had a success rate differ between both the snakes and between the predators? So, like, for every strike, how often does the species get a mouse? And like for every swoop, how often does an owl get a mouse?
So it depends, of course, on the rodent population that we're talking about. It changes drastically based on your physical adaptations. So if you're a kangaroo rat, you probably have a better chance at getting out of harm's way. All of these rodents have inner ear bullae that allow them to sense changes in frequency and in air pressure and hear the predators approaching like an owl. So they can have some sort of a response ahead of time to the owl that's very, very short. My guess is, if you are a pocket mouse, your chances of getting eaten in any of the cases is greater than if you were a kangaroo rat. So the kangaroo rats being bipedal and the pocket mouse being quadrupeds, they have a much lesser ability to get out of harm's way. If you're a quadruped, you have to move forward or sideways, and you cannot jump as well as a kangaroo rat can. So to avoid a snake, you have to jump backwards, because a snake can only attack a third of its length of its body, and at a 45-degree angle from where it's actually positioned. So in order to avoid that, you have to jump backwards. If you cannot jump backwards, you're in harm's way. So there's a higher chance you're going to get killed. If you're an owl can only change its angle of attack as front and back. So if you can jump sideways, you can lower the risk if you're the rodent. But generally speaking, snakes have a much lesser success rates at attacking. You have a better chance of surviving a snake attack than you do surviving an owl attack.
This is, I guess, a bit incidental, but would you define eyes and woodpeckers as convergent species?
That could be an intertaxon competition, and not necessarily convergent of evolution. They may be filling the same evolutionary niche, but we don't know. So this is probably more an intertaxon competition than it is directly convergence. Yes?
You partially answered my question, but I want to go ahead with the rest of it. I did notice that the whisker lanes were different than taxa, based on the illustrations.
Pardon me?
The whisker lanes.
Yes.
The first thing were different. So I was wondering, and you mentioned the ability to detect air pressure.
Yes.
But how about olfactory senses? In other words, how do they know, besides seeing, that this is the snake that they should avoid, or this is an owl's coming, or this is a fox? They have to have, especially if they're going out at night, they have to have some way of knowing.
Yes, so there's a few things. One of our main perceptions, based on work by Amos Costilla, was that the rodents perceive the scent of the vipers based on oils they leave in the sand. And in his experiments for his own doctorate, it showed that the kangaroos were approaching an area that had scents that he actually rubbed the snake in the sand, and it would turn back and move away from that area. They can perceive the risk of predation from vipers by the scent of it. Assuming they probably evolved with it and can recognize the scent from experience. So we don't know if it's learned or it's actually already intrinsic and instinctive to respond to the snake, to the smell of the snake. We're not exactly sure of that. I did test the perception of risk based on olfaction during my master's degree. It was Drobillus allendii, and where I did find that the humidity and heat changed the way they perceive the risk from vipers. That did change. That answers the question.
Because I was curious about their different abilities to that scent of the snakes. The novel one has a scent they don't know. The new one, and the other one has a scent that they do know. In both cases, is there a difference among these rodents in their ability to take any sense at all, or again, detect air? Is there a? Because this is what I was saying was this.
It's a compilation of a lot of different cues to the predation risk, be it olfactory, being sound, some vision also, of course. That's the whole prospect of the work of not only the vipers being able to see them, but their own ability to see it during dark nights also is of course compromised during the new moon. So those different perceptions do change the way they perceive the environment and the risk. Charlie.
So first and foremost, great job. I have a quick question about your experimental design. So did you have like a single owl, or did you have multiple owls?
So we actually had 4 owls. 4 owls, and we switched the owls on every night that we had an owl, and we rotated the nights. So there were no 2 consecutive nights. Sorry, no 3 consecutive nights with an owl predation.
Similarly with the fox or
the fox, we only had 1 fox, unfortunately, but we also removed it from the rest of the experiments. We only did it with the first one for a predator facilitation experiment that Sharon and I was running.
Were there owl-to-owl variability in the responses of the orders?
So I'm not sure about owl-to-owl. Overall, we had a preferred purchase, there we go. So the different purchase that the owls preferred in the vivarium. However, they seem to be the same ones no matter what owl it is. But something about the location of the perch. There's one location behind a big lamp we have in there, which I really like sitting on. And you can actually see that pattern the best with the experiment with Drobillus allendii. There. Oops. Small distance. Push that slide. So, wrong one. There we go. So you can see there's actually a pattern that's very clear between the 2 perches that the owls really like, which are in this corner and this corner. And that also perhaps explains why with the GP, the Drobillus pyramidum, the predation risk was the highest. The actual predation success of the owls was the highest in the control quadrant, which was this area here. For them.
Sorry, so how did you make those maps?
Sorry?
How did you make those maps?
So these maps are generated by a smoothing effect based on location, using a distance-weighted least squares analysis, which is similar to what has been used in multiple papers doing landscapes of fear. So a paper by Cecilia Irigaran with the IBEX instead of code, and a couple of other papers that use that same smoothing effect.
How many trays are in each one of those graphs?
So 48 trays in each of those graphs. Other questions?
If there's no further questions, before we have a final kind of regulating seminar on this, just a couple things then for the committee. We will rendezvous in about 15 minutes. So in 15 minutes, let's rendezvous over at SES 3362 for the people. And if Bert and Jill are there, whether they're there or not, we'll get you on Skype then in 3362. For the rest of everybody else, if you'd like or can join us, we'll probably be leaving here about 5:30 to walk into Greektown. Probably making for reservations about 5:45 at Karen's on Green. That's actually in Halstead and Adams, just on Adams Street, a little bit west of Halstead. Karen's on Green. Sonny, thank you very much.
Yeah.